Hello and welcome to the screencast for Chem Activity 37, Overview of Organic Reactions, subtitled, What are the main types of organic reactions in biological systems? I am Dr. Michael Garut, and this is a screencast for Allied Health Chemistry, Chemistry 120 at Missouri Southern State University. This activity is an application activity. It starts off by giving 7 types of organic reactions, 7 classes of reactions. One of these we have seen before. So the one we've seen before is the acid-base reaction. The acid-base reaction is the transfer of a proton, also known as a hydrogen ion. The other ones are new, and as it says here in the information section, they are in pairs. So we have addition and elimination, which can be considered to be the reverse of each other. We have reduction and oxidation, which we have actually also seen before, but we'll revisit and expand on that in this activity. Those are also, you can also consider them to be the reverses of each other. And we have condensation and hydrolysis. Again, that can be considered to be the reverse. One is the reverse of the other. So let me just take a minute or two and point out some highlights from the 3 pairs of reactions. So if I start with addition and elimination, the way that we describe an addition is an addition of a small molecule, usually water, across a double bond. The across, you can see how that is symbolized. You have a double bond here, which is an alkene. This is also called a site of unsaturation. It's unsaturated because you can possibly bond more groups to these carbons. And that's what happens in the hydration. From the H2O, you bond the hydrogen to one of the carbons, the OH to the other carbon, and now that's considered to be an addition of water. And so I've shown that explicitly here, although we don't always show hydrogens like this. So if I wrote it CH3, CH2, CH2OH, that's a condensed structure of this, and something that you would want to be able to do would be able to recognize what kind of reaction has occurred, even when it's not explicitly shown out like it is here. So that's the skill you're working on here, is to be able to identify the type of reaction that's occurring. In this class, I'm not going to ask you to do much in the way of predicting organic reactions. That's an advanced level skill. I'm mostly going to ask you to be able to identify them. So if given a reaction, you say which kind it is, or if told which kind of reaction it is, to then predict what the products would be, but not from scratch. So elimination is, in this case, the exact opposite of the addition, where you start with something that already has an H and an OH. You remove a small molecule to form a double bond. And here's something you may not have seen before. We have catalysts or reaction conditions just written over or underneath the reaction arrow. And this is just how organic and biochemists describe what the conditions that are necessary for that reaction. They're not part of the balancing of the reaction. They might be a reagent, like H+ is actually a catalyst. Here it says you need to have concentrated acid and you have to heat it. So those are the conditions, but they don't figure into the stoichiometry or the balancing of the reaction. Okay, we've seen reduction and oxidation before, and we've seen how to assign oxidation numbers, but when you do organic and biological reactions, the assigning of oxidation numbers is very challenging, and so it's easier to use these shortcuts, such as addition of 2 hydrogen atoms or removal of an oxygen atom from a molecule. And here I have a molecule. I'm adding H2, that's 2 hydrogen atoms, although they're connected together into one molecule of hydrogen. And here I didn't explicitly show the hydrogen atom connecting to each of these, right? I just went ahead and showed them being attached. And now we have oxidations, and we actually have 3 examples of oxidations because alcohols are a functional group that is commonly oxidized. So if an oxidation, as we've seen before, is an addition of an oxygen atom or removal of 2 hydrogens, which is just the opposite of the reduction, in the bold face, it's kind of showing you where those things might happen. So if I just keep accounting of the oxygens and hydrogens in ethanol, there's 2 hydrogens that are in boldface, and you notice that those are missing here in the acetaldehyde. So we've lost 2 hydrogens, and we've made a double bond there between the carbon and oxygen. The next step is that we add an oxygen, and you can see that extra oxygen added there. When we put an R in brackets or a little lowercase o in brackets, that's indicating reduction or oxidation. It's just a shortcut to symbolize that. A primary alcohol, if you don't remember, is one in which the carbon that contains the alcohol group is bonded to one other carbon. That makes it primary. And we sometimes symbolize that, a 1 with a little superscript like a degree symbol, like first degree or primary. This one, the next one, we could symbolize with a 2 with a degree, which is a secondary, and that indicates that the carbon that contains the OH group is bonded to 2 other carbons. And in that case, we can only do this first oxidation by removing the 2 hydrogens to get the double bond. That's a ketone. But since it doesn't have the H attached to it, it can't go on to make the acid by putting another oxygen in there. So that reaction finishes right there. And if you try this with a tertiary alcohol, symbolized like this, the OH that's attached to the carbon that's attached to the OH is also attached to 3 other carbons. So that's 3 is tertiary. And you can see the difference. In the primary and the secondary case, you can form a double bond between the carbon and oxygen because you can remove these 2 hydrogens. In the tertiary case, there's not a hydrogen on this carbon to be removed, and so it just doesn't work. And another common functional group that gets oxidized are thiols. Thiols, such as this one, which is methane thiol, can be oxidized to make disulfides. If we, I actually think this should not be plus water, but should be plus H2, because we're noticing that we lose an H, and there's 2 of them, so we actually lose 2 H's, and then we hook those sulfurs together. So if I imagined to draw them like this, and the other one in the opposite direction like this, if I were identifying the hydrogens that were being removed, it would be these, and then we hook the 2 sulfurs together to get a disulfide. That is a very common reaction that happens in your proteins. And finally, we have the condensation and hydrolysis. So condensation, coupling of 2 molecules with the loss of a small molecule. This coupling means that you're joining them together. So the typical functional groups here are carboxylic acids and alcohols. And if I draw them in this particular way so that the OH groups are near each other, then it's easy for me to see the small molecule that can be removed. Well, what is the small molecule? It's H and OH, and that makes water again. And then I just join this part with this part, and I get a new functional group, which in this case is an ester. That is called a condensation. And condensations are the reactions by which pretty much all of the common food molecules are made, and we'll see that as we go into the biological chemistry section. Carbohydrates, proteins, lipids, and even nucleic acids are formed by hooking molecules together in condensation reactions. The reverse of a condensation is a hydrolysis, which instead of joining two molecules and removing water, we add water to split the molecules. So we take the molecule, we add the water, and we split it. So if we see in the condensation, the new bond was formed here. When we split that, we're going to split that bond, and then we're going to put the H on one side and the OH on the other side so that we get back the functional groups, the acid and the alcohol functional groups that we had. All right, so that's just kind of hitting the highlights of the types of organic reactions that we're going to see. And then there are a bunch of questions that require you to look back at the definitions and tips about identifying them and then answering those. So let's look at number 1. For the acid-base reaction in Table 1, identify the acid and the base on the reactant side and the conjugate acid and conjugate base on the product side. Draw a line to connect conjugate acid and base pairs together. This should sound familiar to you. We've done this lots of times. So pause the video, connect your conjugate acid and base pairs, and identify each of the 4 as the acid or base or conjugate acid or conjugate base. Pause now. All right, so my guess would be that you've gotten pretty adept at doing this. An acid is the thing that gives up a proton. So this proton has been lost on the product side. So that makes this the acid and this one the conjugate base, and connecting them together with a little line. If this is the acid, and by the way, what is this molecule? By way of review, what's the functional group and the name of this molecule? This is phenol, right? This is water. If phenol is the acid, then water must be the base. How do I know it's a base? Because it picks up the proton to give me one more hydrogen ion and one more positive charge, and so that's your conjugate acid. All right. On question 2, what I'm going to do is just pause the video and then give you my answer for each of these questions A through G. So what you should do is each time you should pause the video, you should look at the reaction, go back and look at reaction types 1 through 7, and then figure out which one you think it is. So if you think it's acid-base, then you would write acid-base right here. Then unpause the video and see if you agree with my answer. If you do agree, great. If you don't agree, pause the video again, look at my answer, and then go back. Look at what you chose and look at what I chose, and try to figure out why I chose what I did and that's correct, and what it was that you were looking at in yours that wasn't correct. So let's start that now. I will move this down so that they're all on the screen. And then every 3 or 4 seconds, a new one will appear. So just make sure you pause each time, figure out each one at a time, go back and look at each of them one at a time, make sure you've got it right before you unpause the video and move forward. So pause now. Okay, did you get reduction? You may be noticing some squeakiness to my voice. I apologize for that. I've had a really nasty cold for the last week, and these screencasts may be a bit late. I'll probably won't be able to get all 6 of them done by Saturday, so I'll probably put them up in stages. All right, pause for letter B. Pause now. Okay, I got hydrolysis. I'm reacting with water, and I've split this bond, and I've added the OH to one side, and I've added an H to the other side, but this molecule has then been turned around so that the N is facing to the right. So maybe that threw you off. But we've added one of these hydrogens and this OH. All right, pause and do letter C. Pause now. All right, hopefully you got elimination. One thing I wanted to point out on this one is that this reaction is not balanced, and that's often done when we're writing organic reactions because we're mainly concerned with the organic molecules that are involved, and we're not concerned with the other inorganic molecules like water or hydrogens. You can tell what's happened is I formed a double bond between these carbons. I've lost this OH group, and I've lost one of these hydrogens. So I've lost water. So you could write plus water as a product here. It's not done. So you should be able to recognize that even though the other product, water, is not shown and the reaction is not balanced. It's time to do letter D. Pause now. Ready for E? Pause now. Okay, did you get this one? I know it's an oxidation for 2 reasons. I have an extra oxygen, so that's adding an oxygen, but I've also lost the 2 hydrogens that were here. So I've lost 2 hydrogens and I've added an oxygen. That's an oxidation reaction. Time for F. Pause now. Okay, did you get this one? This is an acid plus an alcohol, just like the example given in the condensation above. And letter G. Pause now. All right, and we have addition. Addition of water, an H added to one carbon, and an OH added to the other. We didn't show the H added because we don't have to, but there are actually 2 hydrogens there where there was only one over here. There was one here, and there's also one here. But the shortcuts don't show all the hydrogens. All right. Number 3. Classify each of the molecules as primary, secondary, or tertiary. Remember, the way you do this is look at the carbon that's bonded to the alcohol group, then count the carbons that that carbon is attached to. We'll do this one just like the last one. So do letter A. Pause now. Okay, I'm using the abbreviation for secondary. Do letter B. Pause now. Okay, you weren't tricked by this one, were you? It's primary. That carbon is attached to one other carbon. Do letter C. Pause now. Also primary. And now letter D. Pause now. All right, so that one is tertiary. So number 4 says, for each of the alcohols in question 3, show the oxidation products, if any. If the oxidation takes place in 2 steps, show the product of each step. So if you look back at the examples, the primary alcohols take place in 2 steps. The secondary take place in 1 step. The tertiary, well, you'll go back and see. What do they do? So let's do that the same way. I will write the answers for A right here in this space. You can do the same or write it wherever you have space. Pause now. So I'm saying this alcohol gets oxidized and it becomes this ketone. This is a secondary alcohol. I've lost this H and also one that was here. And now I get to this product. Do you see it? All right, pause and do letter B. Pause now. So this was a primary alcohol, so its oxidation takes place in 2 steps. First, we make the double bond between this between this O and this carbon. So I've lost this hydrogen and this one to create a double bond there. And then I've added an oxygen in the second step. Now, this might look kind of strange, and it looks strange to me. When we are drawing an aldehyde, which this is, I feel like we almost always go ahead and draw the hydrogen there that we sometimes don't, just so that it's clear that you have a hydrogen on one side of that carbon and then a carbon on the other side, so that in the second step of the oxidation, we are adding the oxygen between this H and this C right there. And that is a carboxylic acid. And if you drew it like this, it would be the same thing. Just rotated, where this oxygen is just rotated up here around the single bond, and that's the same one that we have seen before. That's benzoic acid. 2 different conformations of benzoic acid. Or probably not even 2 different conformations. These are probably identical because you could just turn your head over and look at it a different direction and see it like this. All right, pause and do part C. Pause now. Hopefully you recognize that this one is exactly the same one as the one in the example. This is ethanol. This is acetaldehyde. This is acetic acid. It's the exact same one shown in Table 1. All right, pause and do part D. Pause now. Okay, that one's easy. That's a tertiary alcohol, and so that's no reaction. These do not easily oxidize. Can you oxidize tertiary alcohols? Under really harsh conditions, but it's complicated, and under these normal conditions, no reaction. That's the end of this activity. So now you have some exercises where you practice these some more. Do them one at a time. Check your answers with the ones on the exercise solutions category of Blackboard. And hopefully you have a good feeling for these reactions. I will point out that here's some information given in the middle of the exercises which summarize up the functional groups that are commonly found in these types of reactions. So, for example, with the oxidations we've just been looking at, what functional groups are typically involved in those are aldehydes, primary and secondary alcohols, but not tertiary alcohols, because tertiary alcohols don't easily oxidize. So this is just some helpful information so that you can see what are the typical functional groups that are involved in those. As usual, do your answers one at a time, check them on Blackboard, and you'll be ready for the next chem activity. This concludes the chem activity screencast for activity 37. Cheers!